we've got alcohol A, and it's asking for a name. I always think it's best if you sort of draw it out really. First of all, either it's displayed or some kind of condensed structural formula here. So I've got CH3 twice, there you go. I've got CH, so I've got a C here with an H off it that's not seen on that skeletal section. I've got a CH here, so I've got a C with an H off it again that's not drawn on the skeletal section. You could draw the C's with the H's. Then I've got an OH hanging off this C, and I've got a CH3. So now I can see it, I can see what it is. So its longest carbon backbone is 1, 2, 3, 4. So it's some kind of butane. And if I go from this side here, it's butan 2-ol with a methyl. It's 3-methyl butan 2-ol. Draw the structure of the organic product B formed when A is oxidized in the reaction with acidified potassium dichromate. So the OH turns to a double bond carbon to oxygen. So you get a carbonyl group, a carbon to oxygen double bond where the OH is. That's what happens with potassium dichromate. So the OH turns to the C double bond O, and that carbon that's got an H as well that's unseen on that skeletal formula loses that. So it loses an OH and the H, and it just becomes C double bond O, and then it bonds as normal to the other carbons. Two isomeric alkenes are formed when A is dehydrated. So dehydrated is removal of water. So what it does is it removes the OH from one carbon, from this carbon here, and it removes an H from the adjacent carbon. So it's going to remove the OH from this carbon, and the adjacent carbon here, this carbon here, is going to lose an H. So that's going to become CH2, and this is going to lose an OH, and there'll be a double bond between these two here. Alternatively, it could lose the OH and go the other way, because this carbon's got an H on it as well. So this carbon could lose its H, the H that's hanging off this carbon here on the skeletal formula. It could lose an H and this OH and form a double bond this way. So your reaction can form a double bond between the two carbons here in the middle, between these two carbons, and it takes the H off this C here, as well as the H off OH off this C. Remember, this C is still going to have an H here, so it's forming a double bond between the two here. Or it could form a double bond here, take the OH off here and one of the H's off there, and could form a double bond here. It's called elimination because we're removing water. So it's called an elimination reaction because we're removing H2O from the structure. Name the type of structural isomerism shown by C and D. So we've got some kind of 1, 2, 3, 4. We've got some butene, 2-methyl butuene, and I've got 3-methyl but1ene here. So I'm changing the position of the carbon-to-carbon double bond. So it's some kind of structural isomerism. It's not chain isomerism because I'm not shortening the chain. It's not functional group isomerism because there's still a double bond in there, that's still the functional group, but I've changed the position of the double bond. So it's structural isomerism, but more specifically it's position isomerism. List the alcohol A, product B and C in order of increase in boiling point. Alcohol A, product B and product C. So let's have a look what I've got. Alcohol A. Well, alcohol A has got an O bonded to an H, so it's got hydrogen bonding, so that's going to have the highest boiling point. Then product B has got a C to O double bond, so that's going to have a polar bond, so it's going to have dipole-dipole intermolecular bonds. That's the next highest boiling point, and these have just got no polar bonds at all, so these are just going to have van der Waals bonds. So this one with hydrogen bonding is going to have the highest boiling point, and then product B is going to have the next highest boiling point because it's got a polar bond here, so it's going to have dipole-dipole intermolecular forces, and these have got the lowest boiling point with van der Waals. Draw the structure of the isomer A that is not oxidized by acidified potassium dichromate. So you're looking for an OH on a carbon that's got 3 other carbons bonded to it. So potassium dichromate will oxidize primary or secondary alcohols, but it won't oxidize a tertiary alcohol. A secondary alcohol, like the one in the question, will turn into a ketone, and a primary alcohol will turn into an aldehyde, because the OH is at the end at carbon number 1, turn into aldehyde, and if you carry on heating it with potassium dichromate, eventually it'll turn into a carboxylic acid as well. But anyway, the question is saying which one is not oxidized, so I'm looking for a tertiary alcohol, so I'm looking for an OH bonded to a C, and therefore I can only have a methyl group, and to make the right number of carbons I can have an ethyl group here. Draw the structure of the isomer A that cannot be dehydrated to form an alkene. So you're looking for a C with an OH, and the carbon bonded to it either way has not got an H. So let's have a look at this one. So you've got CH2OH. So the OH here bonded to a C, yeah, needs an adjacent carbon to that carbon with an H, and it hasn't. So you draw out the CH2OH here, and then you put a C, and then you join other carbons off it, and there must be 3 methyl groups to make up the number of carbons. So there's no way that OH can be removed because I'm looking for an H on the adjacent C. There's no C's to the right, the only C is here, and it hasn't got an H to remove. So I'm looking for an OH and an adjacent H on 2 carbons, which would then come off on an elimination reaction and leave a carbon-to-carbon double bond in the middle, but it can't do.